Both the sections, can you see the screen?
Yes, ma'am.
Yes? Both the sections, can you see the screen?
Yes, ma'am.
Yes, ma'am.
Yes? Can you hear me,
Yes,
guys?
ma'am. Yes, ma'am.
Both the sections, can you see the screen?
Yes, ma'am, we can see the screen.
Guys? Yeah. Okay. Yes, ma'am. G section. Dhanush, can you confirm me? Can you see the screen? Yeah. Okay. Fine. So now let's discuss today's. And moreover, some of you are saying that still we are not able to join. Guys, whoever has updated their email IDs, to them I have already sent the invitation. So whoever has got the invitation, only them can attend the class. Later, if they're asking us to join, I'm not allowing them. Okay? So please update your email IDs. That's the reason I told. If you get a link from your friends also, you can't join the class. So this is for your kind information. Later you can't just come and tell me. Okay? And some of you might have updated your wrong email IDs, because of which you might have not received the email. So just go back and check your email IDs. I'm repeating, I'm not extremely taking them in the class. If you're joining with the invitation, then only. Okay? So please consider this as my request. Please do join with the invitation only. And if you're not getting the invitation, just do inform me before the class, not on the class itself. That time I can't do anything. Okay? So this is what I wanted to convey you all. Now after the class, don't expect to join. So anyways, I think in the last class we have discussed up to the above example. So today we will go ahead with the next thing. Okay? So here, directed graphs of relations on the set. So this is what we are supposed to deal with. So here you can just observe that this particular thing, the directed graphs of the relations. The directed graphs means I actually explained to you how the graph we are supposed to draw. So here, whatever the relationship they have given with, so let R be a relation from finite set to itself if they have given, okay, and just a minute, yeah. So they have given, so here there is R is a relation from one finite set to itself. So from one set to that itself, set itself they have given. If that is the case, then we write down the elements of the set and then we draw an arrow from each element x to its each element of y whenever x is related to y. This diagram is called as directed graph of the relation. So directed graph of the relation means, suppose here in this example, if you observe, here they have given that A is equal to 1, 2, 3, 4. And they have defined the relation from the set A to set A itself. From the set A to A itself like this. So R is a relation 1, 2, 2, 2, 2, 4, 3, 2, 3, 4, 4, 1 and 4, 3. So this is the relationship which is defined on the set A to set A itself. So how do we draw the directed graph for this particular relation? That's the question. Now I'll write 1, 2, 3, 4. So clearly you can see 1 is related to 2. So from 1 to 2 we have a relation. So this is the arrow mark which you can see. Now from 2 to 2 you have a relation. So this the cap, you can see the cap arrow, that is 2 to 2 means 2 is related to 2. So this is the graph. Similarly 2 is also related to 4. So 2 is related to 4. So this arrow mark. Similarly you have 3 is related to 2. So this is 3 which is related to 2, this arrow mark. Then 3 is also related to 4. So 3 is also related to 4, this arrow mark. And they have given that 4 is related to 1. So this 4, it is related to 1. So this is the arrow mark. And 4 is also related to 3. So this again, in turn, we have relation. So 3 is related to 4 and also 4 is related to 3. So this is how we can draw the graphs which are called as directed. Directed means it is showing the direction. So with this direction, you can tell that yes, 1 is related to 2, 2 is related to 4. With this direction, you can say yes, there is a relationship Without actually seeing this, if you see this graph also, you can identify from which element to which element there is a relationship. Okay, so that's the reason this directed graph are a simpler way of explaining the relationship. Okay, so next you have the composition of relations. So what is the composition of relations? So here, suppose there are A, B and C sets, and let B, there is a relation from A to B, and let S be the relation from B to C. So there is a relation A to B and there is a relation B to C. So now R, I am taking a relation which is a subset of A cross B. A cross B means the Cartesian product of A cross A and B. That is the whatever the subset I am getting from here, that I will take it as R. And S is the subset of the Cartesian product of B and C. Okay, so this is another relationship. Are you following me, guys? One of you from H section, one of you from G section, please just text me or you can
Yes,
unmute and
ma'am.
tell me. Yes?
Yes, ma'am.
Are you not able to unmute yourself? Yes? Because I'm not able to see have to go back and have to check your messages. That's the reason I'm just asking you. Are you able to unmute and tell me? Anyone? Yes, ma'am. Okay, Anjana, Priya.
Yes,
I have to
ma'am.
go and I have to check the messages. That's the reason. Okay. G section, Dhanush. Anyone from there? Not able to unmute? You're not able to unmute? Okay, let me see the G section here. It will take little time. You're speaking, but I'm not able to hear you all. But I'm audible. I'm audible to you, right? That is good.
Yes, ma'am.
If I'm not, you can't hear us, ma'am. Okay, no problem. If I'm audible, it's fine. But you don't talk much now. Okay. Yeah. Let me go ahead with the next thing. Yeah. If anything is there, just WhatsApp me. Okay. Yeah. So here the composition relationship means what I was talking about. I'm talking about two relations. One is R, which is a relation on the Cartesian product of A and B. One is relation S, which is a subset of B and C. Now R and S give rise to a relation from A to C. So from A to B, R is a relation. From B to C, S is a relation. So R and S, if I take them together, this composition will give me the relation from A to C. That's why it is called as composition. And it is denoted by R dot S. It is denoted by R dot S. So here you can see the element A from the set A. This is the composition relation R dot S, and this is the C. So A to C. So this is noted like this, which is defined as if for all B belongs to B. So B is an element coming from the set B. This implies that A is related to B and B is related. See, the relation is denoted by S here. B and C relation is denoted by S. A and B relation is denoted by R. Okay, so this is the notation. So by this, the composition R dot S. Okay, so R dot S, it is a composition which is denoted by the, you can see the ordered pair A comma C, such that there exists the element B belongs to B, for which AB belongs to R and BC belongs to S. So it is very much clear that this AC is included, the two ordered pair here. One is AB, which is coming from the R. R means the Cartesian product of A and B, and BC, which is coming from the S, that is nothing but the Cartesian product of B and C. Therefore, this relation R dot S, it is called as composition of R and S. The composition of R and S. Okay. So now we have one note. The composition of R and S is also denoted by R dot S. Let R is a relation on a set A that is R is a relation from a set A to itself. If suppose A to A there is a relation, then R dot R, it is a composition of R with itself. So you should know that not only we are having the composition relation with one set to another, but also we have a composition relation to set itself. That is R dot R, S dot S. They are the composition relation. So here, if there is a composition relation to set itself, we denote it by R dot R, and sometimes we can also write it as R star. Okay, so now see, similarly we can write it as R cube. R cube means what? R square dot R. So R square is nothing but again R dot R. So if you have R4, it is R cube dot R. R cube is nothing but R square dot R, and so on and so forth. So now you can denote n number of relation, Rn composition relation, which is true for all the positive numbers n. So this is the note which you have for the composition relation. Am I clear up to this, guys? If yes, please share it in the box. If I will see what is the technical difficulty, why I'm not able to hear you all. That I will check. It's all exploring every day. Yeah. Okay. So now let's go with the next important thing, that is types of relation. So guys, here we have, and even my writing part is also not working. That's why all this technical difficulties I will check. See, types of relation. So in the types of relation, we have the first one is the reflexive relation. So the reflexive relation means, say, for example, what is the meaning of this? Let us understand first. A relation R on a set A, it is reflexive if A is related to A. That means if each and every element is related to itself. If suppose you are seeing yourself in the mirror, what you are getting? You are getting your own replica. That is nothing but your reflexive. If you are seeing yourself, but you are finding someone else, that means it is something not reflexive. Okay, so something is there. Okay, so here reflexive relation means what? It is the image. Whatever you can see, whatever you are seeing, the same thing you should get back. So here A is related to A, B is related to B. These all are the reflexive relation. So this has to be true for every element there in the given set. That is, if A comma A belongs to R, this is true for every A belongs to A, then R we say. Thus, suppose if that is the case, then we call it as reflexive. And if suppose R is not reflexive, when if there exists at least one A such that A comma A does not belongs to R. If A comma A belongs to R, then it is reflexive. If there exists at least one A belongs to A such that its replica is not belongs to R, then it is not reflexive. Let's see the example. If there is a given set A, that is 1, 2, 3, 4, and there is R which is defined as 1, 1, 2, 2, 1, 3, and 2, 4, 3, 3, 3, 4, and 4, 4. So is this relation is a reflexive relation is the question. If you observe carefully, guys, in this, what has to be necessary? Since it contains 4 elements, so every element has to have its replica. So 1 has to be related to 1, 2 has to be related to 2, 3 has to be related to 3, and 4 has to be related to 4. If that is the case, then only we can say, other than that, any relation may be possible, but this is compulsory. What is compulsory? Every element has to be related to itself is very much compulsory. So clearly if you see, so 1 is related to 1, 2 is related to 2, and here you can see 3 is related to 3 and 4 is related to 4. Along with this, we have different 1, 3 and 2, 4, we have 3, 4, no worry. So since all these belongs to this, and this is true for each element, 1, 2, 3, 4, hence we call it as a reflexive relation. Hence what we call it as? What do we call it as? Reflexive relation. Now similarly, see the example 2. So here, consider the following 5 relations on the set A. So here there is R1, which is defined as 1, 1, 1, 2, 2, 3, 1, 3, 4, 4. And this is R2, which is defined. And this is R3, and this is R4. That is the empty relation. And there is R5 also, that is A cross A, the Cartesian product with itself. So it is also called as universal relation. So if it is empty, it is called as empty relation. A cross A is called as universal relation. So determine which of the following relations are reflexive. That is the question. If you clearly observe from this R1, so here 1, 1 is there, 4, 4 is there, but 2, 2 is missing and 3, 3 is missing because the set A is containing 1, 2, 3 and 4. That means according to the reflexive relation definition, it says that it has to have each and every element's replica. But here 2, 2 is missing and 3, 3 is missing. Hence R1 is not reflexive, though it contains 1, 1 and 4, 4. So you should not be confused. So you should see that each and every element must be having a reflexive relation. Okay, it is not 1 or 2 elements. Similarly, if you see R2 here, 1, 1 is here, 2, 2 is here, 3, 3 is also there, 4, 4 is also there. With that, you have 1, 2, 2, 1, no worry. So therefore, it is again reflexive. Clearly in R3, it is 1, 3 and 2, 1. It is neither has 1, 1 nor has 2, 2 or 3, 3 or 4, 4. So none of the reflexive relations are available here. Hence R3 is also not a reflexive relation. So clearly, what about R4 then? If you see the R4 guys, so this one, R4. If you observe R4, so this R4, it is the empty relation. It is the empty relation. So if it is empty relation, does it have any elements here which are reflexive? It has no elements. Hence, it is not reflexive. What about the inverse relation? So there is an inverse relation, means it contains each and every element. So it is containing every possible relation here. So therefore, it also contains the replica elements, that is 1, 1, 2, 2, 3, 3, 4, 4. So remember, this inverse relation is always reflexive relation. Okay. So therefore, since you can observe from the given R1, R2, R3, R4, clearly only R2 and R5 is a reflexive relation. Other than that, R1, R3 and R4, they are not reflexive one. And even I have explained you the reason also for that. Okay, just go with this reasons. Now next we will get to the irreflexive relation. What is the irreflexive relation? Let's see it. A relation R on a set A, on a set, it is called as irreflexive if A comma A does not belongs to R. A comma A does not belongs to R. This has to be true for every A belongs to A. It is not only for one element. It has to be true for each and every element. That is for every A belongs to A. Thus, R is, then we call it as irreflexive. It is not irreflexive when, if there exists at least one A belongs to A, such that A comma A belongs to R. So what do you mean by that? Here you can see, in this particular example, this 1 comma 3 and 2 comma 1, this is a relation where none of you have neither got one of, at least one also, there is no reflexive relation. So this example actually meant for irreflexive one. So if there exists at least one means you can observe this example R1. So there is 1 1, there is 4 4. So there are two elements which are having the reflexive relation. So it is not irreflexive. So this is not irreflexive. So here there should not be any. So that's the meaning. A relation R on a set is irreflexive if A comma A does not belongs to R. This is true for every A belongs to A. So if there exists at least one also, then it is not irreflexive. Okay. So there is a difference between not reflexive and irreflexive. In irreflexive, no single element is allowed. In reflexive, each and every element has to be there. So here I have shown you all the examples. So this is the reflexive example where you have got 1 1, 2 2, 3 3, 4 4. So all the elements are reflexive. Here you have got, see, 1 1, 4 4, but still it is not reflexive. At the same time, it is not also irreflexive. But R3 you can see 1 comma 3 and 2 comma 1. So there is not even a single element which is having the reflexive relation. Hence it is irreflexive. Okay. So please remember between the difference between the reflexive, irreflexive and not reflexive. Okay. So that don't confuse here. So make it very much clear. So clearly, let's example, if they have given you here, probably let us consider R on a set A such that R is equal to A comma B such that A should not be equal to B. So if A is equal to B, then A comma A, you will get it. So here R is the relation of inequality on a set A. Thus, R is irreflexive since for every A belongs to A or A in A comma A does not belongs to R. Okay, so the same way the explanation is. Similarly, you can see here A, B, C, there are three elements. Let R is the relation A comma A. Here R is not reflexive because I have to have B comma B, I have to have C comma C also. Since B comma B is not belongs to R and C comma C also not belongs to R. And R also is not irreflexive because it contains A comma A. As per the irreflexive, it should not contain any element of that kind. So then it is neither irreflexive. So this is another example. So don't confuse, again I'm telling you, reflexive means each and every element, whatever the element you have in the set A has to have its replica. Irreflexive means there should not be any element of the type replica. Okay, so at least one also exists, then it is not irreflexive. Not reflexive means if at least one or two are existed but remaining are not there, then it is not reflexive. Okay, so like that. If you just see the problems, you will get it. You will get the more clarity about it. Okay, so then hope up to this it is clear. H section, someone can just chat it and tell me. Is it clear up to this point, guys? Just chat it. Yes, Vedanta has texted me. And in G section,
Excuse
can
me,
someone just text me?
Excuse me.
Govind, I'm recording H section meeting. Don't worry, I will send you. Huh, beta? Only one meeting I'm recording because it will be taking much. It will take the more MB in your words, and because of that, my drive is syncing. Okay, that's the reason I'm just recording only one meeting, either G section or H section. Okay, yeah. So let me continue with this. Yeah, then we have something called symmetric and antisymmetric relation. Let's see what is this. So a relation R on a set capital A, it is symmetric if whenever A is related to B, then B is also related to A. So for example, if Arun is a friend of Kiran, then Kiran is also a friend of Arun. So like that, vice versa. Okay, so that way a relation is symmetric if A is related to B, then B is also related to A. Whenever AB belongs to R, then BA also should belongs to R. Then we call it as symmetric. And R is not symmetric. If R is not symmetric, if there exists AB belongs to A such that this A comma B belongs to the element A such that AB is in R but BA does not belongs to R. If that is the case, then we call it as not symmetric. We call it as not symmetric. Okay, so symmetric means if AB belongs to R, then BA also should belongs to R. Let's see some example here. So determine which of the following relations are symmetric. So the given set is, there is a given set A is equal to 1, 2, 3 and 4. So there is a relation R1, there is a relation R2, there is a relation R3 and R4 and R5. So let's see which is the symmetric one, which is not a symmetric one. So let's see. Now if I see R1, so 1 comma 1 is there, 1 is related to 1, 2 is related to 2, 2 is related to 3 and 1 is related to 3, 4 is related to 4. So clearly 1 is related to 1, that means 1 is again related to 1, so no problem here. 2 is related to 2, 2 is again related to 2, no problem. So here 2 is related to 3. Is there 3 is related to 2 available here? No. Similarly, 1 is related to 3, but 3 is related to 1, it is not available in the relation. So similarly, here you can see at least one fails, it's completely failed. So I'm just taking here. So here you can take 1 comma, sorry. So this is not 2 comma 2, this is 1 comma 2. Please make a note. So 1 comma 2 belongs to R1, but 2 comma 1 does not belongs to R1. If any one also you mention, that is enough. So I have mentioned here 1 comma 2 belongs to R1, but 2 comma 1 does not belongs to R1. Hence it is not symmetric. Similarly, you see R2 here. Before seeing R2, I'll just show you R3. 1 comma 3 is there, but 3 comma 1 does not belongs to R3. Similarly, 2 comma 1 is there, but 1 comma 2 does not belongs to R3. Hence, it is not symmetric. Similarly, come to this null set. So here the null set I'll come later. Here you come to R2 now. 1 comma 1 is there. 1 comma 2 you have. 2 comma 1 is also there. Okay, so 2 comma 2 is here, 3 comma 3 is there, 4 comma 4 is there. So all elements, there is a symmetric. Say 1 comma 2 is containing 2 comma 1. So 1 comma 1 means it is 1 related to 1. So 2 is related to 2, 3 is related to 3, and 4 is related to 4. So there is no difficulty. Only 1 comma 2 and 2 comma 1. So both the things are existed. Hence R2 is symmetric relation. Come to R4. So there is no such element which does not exist at all. So which I can tell that this is existed, this does not exist. So there is no such element means it is on the empty set is always a symmetric relation, because there is no such set which you can tell that this exists, so its opposite does not exist. Hence we can consider this null set, or you can say the empty set, for the symmetric one, and even for the transitive also. Okay, so here the universal relation, as you know, it contains all the elements, all the Cartesian product elements, hence it will be always the symmetric. Therefore, out of these relations, you have R2 and you have R4 and R5 are the symmetric one. So let's see what is asymmetric then. Asymmetric means a relation R on a given set A, it is asymmetric. If AB belongs to R, then BA does not belongs to R. It means that R is not asymmetric if for some AB, for A, both AB belongs to R and BA belongs to R. So asymmetric means it is not, here it is asymmetric when this is belongs, this does not belongs. If both belongs, it is not asymmetric, or in other words, it is symmetric. So here you can see, don't confuse, not asymmetric or symmetric, both are one another same. Asymmetric means one belongs, one does not belongs. So here, the example you can observe, ABCD is a given set, R is the given relation. So here you can observe AB belongs to R, but BA does not belongs to R. Okay, hence R is not symmetric. R is not symmetric means what? It is asymmetric. Also you can see BB belongs to R. So here, but here, why it is not asymmetric? BB belongs to R. At least there should be this has to be true for every element. But here BB belongs to R. So BB belongs to R means there is at least one element which is containing this. See, BB belongs to R, BB also belongs to R. So this is valid for symmetric. Here this is not valid, this is not valid. But because of presence of this, even it is not asymmetric. So here, according to asymmetric, this is to be true for every element. If AB belongs to R, then BA must not belongs to R. This has to be true for every element. This has to be true for every element according to this particular thing. But hence, here BB is there, therefore it is even not becoming asymmetric. Okay, it is not symmetric also, it is even not asymmetric also. Okay, since BB belongs to R. And since if A is not equal to B, if A is not equal to B, then you can see either AB does not belongs to R or BA does not belongs to R. If A is not equal to B. So whether A is, if it is A is equal to B, that means A is equal to B means A, B, both will become same. If A is not equal to B, then this also will not be belongs to. Hence, we call this is again even not antisymmetric. So there are some words: symmetric, asymmetric, antisymmetric, not symmetric. So don't confuse. So actually asymmetric is for each and every element. Symmetric is if for every given element, if there is a, let's say, in the above example I explained you, here in this given element, if at least one example, like say 2, 3 is there, 3, 2 also should be there. If 1, 3 is there, 3, 1 also should be there. If that is the case, then we call it as symmetric. But asymmetry means it has to be true for each and every element. Okay, and if this is not existed, if 2, 3 is there but 3, 2 is not there, then you can call it as simply not symmetric. Okay, so just solve more and more problems. You will be thoroughly clear with the concept. Now, if you have any questions, anything, please chat it in the box. I'll get back to you as you are not audible to me. Just H section and don't just leave the meeting. Even I'll be downloading your attendance also. And G section people, from tomorrow onwards, you will be joining with your USN number. So I will send the invitation to that only. Not to worry. Okay. In G section there are 55 members, and in H section there are less numbers. It's just around 45. I'll just check what is the technical difficulty I faced today. Why I'm not able to hear you? I'll check. Okay, guys, then I think hardly 1 minute is left to us. So with this, we conclude today's discussion. So one more time, I'm telling, whoever has not received the invitation, please do inform me well in advance, not on the class itself. So today I will share it again with your the USN ID for G section. For H section, the same email IDs. Whoever has not got the email ID, invitation, please do text me, WhatsApp me, I'll get back to you, or mail me. Okay. So with this, we conclude today's discussion, guys. In tomorrow's discussion, we'll continue with the next concept. Okay. So till then, please take care. See you all shortly in the college campus. Till then, take care, guys.